Okay, so what we're going to talk about in this video is um, a little bit of synthesis. This is something that you guys have seen already. It's of particular importance, and we've seen it a good bunch of times already, and we're going to be seeing it a lot more. So what we're going to look at here is, this is actually question 1619 from the textbook, and I want to see just if I can perhaps clear up any issues that you might have with a question like this, and how you would approach a synthesis like this. All right. So let's see what we can do here. Let's look at what the question is showing us that we have, and what we have to do with it. All right. So we have an alkyl bromide. All right. And what's the functional group that we're making from this? Well, it's an amine. All right, so we're making an amine here. Now, one of the things that you can hopefully see is not only are we making amine, but what in particular are we forming that's going to tell us at what point we have to do a particular reaction. Well, hopefully you've noticed that we are adding a carbon here. In fact, we're forming this carbon-carbon bond. So that tells us we're going to need some sort of reaction that makes a carbon-carbon bond, and the most common one of those that we've seen already, particularly when we have something that already contains a halogen. Sorry if my pen looks a little wonky here. My cat is up here with me, and she is rubbing herself all over everything that I'm trying to use, being a pain in the butt. Yes, you are. I know. Yes, you are. But I love you anyway. So, yeah, if my pen goes all wonky, then blame it on my tripod bloody cat here. Okay? Okay, you can sit down, alright? Alright, you can stand up. Alright, okay, so let's see what we can do then. Okay? Now, one other thing about this question that gives you a little bit of guidance that you wouldn't normally have is, yeah, it tells you this is what you have to do, but I'm not going to tell you how you have to do it. That's what you'll normally expect for a synthesis question, but this one actually tells you how would you use the reaction of an amide with lithium aluminum hydride, in other words, that would be a reduction reaction, as a step in the above synthetic procedure. So this is telling you one of your steps has to be the reduction of an amide. Alright? So, in other words, the reduction of something that looks like this. So here is my amide, and if you add lithium, oh, cat's back again, bloody hell. If you add lithium, aluminum, yeah, okay, Emma. I know, I love you too, but still, let daddy work, okay? If you add lithium, if you add lithium aluminum hydride to this, in its two steps, oh, okay, you're back again, alright. And you add H3O plus to that. What would the product be that you would get? Well, I'm hoping that you recognize that you would get an amine. In fact, you get essentially the same product that you had before, but without the carbonyl group. So, can you also see then, if the amine is the final product here, then the amide must be the product that was right before it. So what this then means is, not how can I go from here to here, because I know how to go to here from this amide, but then how can I go from this alkyl halide to this amide? Alright? So let's see what we can do. We've already said we're going to need a Grignard reaction at some point. Alright, so let's move on to another page and see what we can do. Alright? So we know that we can do this. So I'm just going to draw out the amide. Here's my amide right here. Alright, so we know how to do this. That's our lithium aluminum hydride. So, what are we going to do here? Well, we're starting with an alkyl bromide. We've said we want to do a Grignard reaction. So what do you guys think the first thing is we have to add to this if we want to be able to do any sort of a Grignard reaction? Well, usually this means if we have the bromine here, we've got to insert something in between the carbon and the bromine to make our Grignard reagent. And that something is, of course, magnesium. That makes our Grignard reagent, so we get MgBr here. Okay, now how many carbons are we adding in here? Well, we're adding in this one. These two carbons will add on with the nitrogen, but we're adding in this carbon. And also bear in mind that in the products here, we're looking to have a carbonyl group left over. Now, normally you guys have seen that a Grignard reaction forms an alcohol because the one carbonyl group from your starter material gets broken open, forming an alcohol. So if you want to have in your product a molecule that contains a carbonyl group, that means whatever you add in here has to have had two carbonyl groups. And there's only one species that I know of, and I'm sure that you guys know of, that allows you to add in one carbon and has two carbonyl groups. Well, if you just try and draw it out, well, okay, one carbon, one carbonyl group, two carbonyl groups, oh, CO2. And what's the last step in every Grignard reaction? Always the, sorry, that's kind of messed up. Always the last step, it's always H3O plus. Okay? So what's the functional group that we get out after we do these three steps? Well, it's a carboxylic acid, and it actually looks like this. Well, it should look a little better than that, but anyway, it looks something like that. Could you guys name what this is? You remember the naming convention for cyclic carboxylic acids? It's actually quite simple. This is cyclohexane carboxylic acid. So then all that's required is how do we go from the acid to the amide? We know how to go from an amide to an acid, just acidic hydrolysis, but we want to go the opposite way. Well, hopefully you guys can see that this is the guy that we want to remove. And we also know this is a crap leaving group. So if we want to replace this by this, we've got to replace this with something that's a very good leaving group. And we've seen several times good examples of great leaving groups, and probably the most common of those are the halogens. You guys have seen already that if you go from an acid to an acid chloride, the reactivity goes way up, which is what you want. Simply because this leaving group here, this chlorine leaving group, is great and the OH is bad. But that requires us to know, well, how do we go from here to here? What is that reagent? Well, if you can remember socket to me, you are part of the way there. Socket to me to SOCl2, thionyl chloride. Sometimes you'll see pyridine written here as well, as just a base to mop up the chloride ions that come off. However, I'm not particularly picky about that. You'd have to do it in practice, but on paper, SOCl2 works just fine. Okay. In that case then, how would we go from the acid chloride to the amide? Well, if this is a great leaving group, then we just need our nucleophile. And you can see our nucleophile has got to contain all this. It's got to contain nitrogen. It's got to contain two methyl groups. But you and I both know nitrogen doesn't like just two bonds, it likes three, so we can add our third bond here with just a hydrogen. Alright, so that's just an acid chloride, an amide, an acid chloride and an amine going to an amide. And when we add in our last two steps here, lithium, aluminum hydride, and then the second step of H3O plus, then you'll see that we've actually done 1, 2, 3, 4, 5, 6, 7. Man, that's 7 steps. That's a 7-step synthesis. Now, how likely do you think you would have been able to do a 7-step synthesis? Because that's actually quite long. In practice, that's a hell of a synthesis to do. Because 7 steps in practice is not easy to do. We're going to be doing something like this in lab, but nowhere near as complex. But anyway, that is an example of how you would apply synthesis using the reactions that we've learned most recently. Okay? All right. Thank you. You remember these pretzels are making me thirsty comment that I put at the end of one of my previous videos? Well, I'm thinking about putting something weird and quirky at the end of each of these videos. Of course, that would mean I could have really planned something to say here. So,